Hi guys, I'm Professor Student and welcome to the first instructional video I am putting up on YouTube. So a little bit about me, like my name insinuates, I am also a college student and as many of you may be. And I'm making these videos because I know sometimes people may have trouble understanding concepts or just may want to learn more about concepts. And maybe sometimes the way your professors teach them or other instructors on YouTube may teach them may not really comprehend with you. And so I hope that as from one student to another, I can really help you guys on your journey through all these STEM subjects. So enough said about that. This video is going to be the first video I'm making. So I know that I may still have some improvement based on how I teach or whatever. So if you guys think you have any constructive criticism or any advice you can offer me, I'm all ears. So please just leave a comment. And I'll definitely always try my best to provide the best quality instruction I can for you guys. So enough said about that. This first video is going to be on molecular bonding, hybridization, and atomic structure, and is going to be the first video in a series of organic chemistry videos. So what is organic chemistry? Organic chemistry is a branch of chemistry that studies the properties and reactions of organic compounds which contain carbon. So simply put, I guess organic chemistry is essentially the study of carbon, because carbon is honestly one of the most fundamental elements in our universe and is also one of the most versatile. You may have heard before that we are all carbon-based life forms, and honestly, that is the truth. If you guys are interested in going into the medical field, or if you're interested in going into the pre-health field, biotech, pharmaceuticals, etc., organic chemistry is a must for you guys. So I think it's really important that you guys understand these concepts and are able to apply them. That being said, this first video is an intro to organic chemistry, but contains topics that have already been covered in general chemistry. So if you guys have already taken those classes or feel comfortable with the topics that are coming up ahead, feel free to move on to the next video. But of course, if you guys don't understand these topics yet, or are just looking to learn something new, that's what this video is for. So let's start. So here you can see the periodic table. So what is the periodic table? So the periodic table is essentially a collection of all the elements that we as humanity have discovered. So first off, what are atoms? Atoms are essentially our molecular building blocks. Right? So atoms are made of three main components: neutrons, electrons, and protons, which I assume most of you guys have heard of, at least briefly. Of course, we won't really focus on anything smaller than those, such as quarks, because that's more of a physics or quantum physics topic. So we'll kind of stop there. But anyways, so we have two elements in particular that we tend to focus on in organic chemistry. And those elements are hydrogen, our first element on the periodic table, and carbon, which is our sixth element. Right? So yeah, these two elements are honestly the most commonly studied elements in organic chemistry. So a breakdown essentially is we kind of go from electron configuration then we go to the bonds that these elements make using those electron configurations. Based on the electronegativity of those bonds and elements. To the bond polarity. And finally, to their reactivity. So let's take a look at our periodic table here, right? So you may notice this, and I hope you guys know some basic information about the periodic table. But for instance, let's just look at some of the trends on the periodic table, the most important being electronegativity. So you guys may already know this, but just in case, the trend for electronegativity, is electronegativity increases as you go to the right and as you go up. Okay, so that means our most electronegative element here is fluorine. And you may be wondering why the elements in this last column aren't considered the most electronegative, but that's because they're noble gases, which means they don't tend to react with other molecules because they already have a full octet of electrons and don't really have any need to bond with other molecules. So finally, one last thing I guess before we continue is there's different blocks in the periodic table, and the most important that we tend to focus on for the sake of this class mostly is the S block and the P block, right? So the S and P blocks are just different blocks of the periodic table that we'll be focusing on throughout the course or just in general. So finally, there's also something called electron configuration, which I mentioned over here. So what is electron configuration? That's essentially how the the electrons are arranged in an element. So for instance, if we see carbon here, right? Carbon is our sixth element, which means that carbon on average usually tends to have 6 electrons. So how are those electrons arranged? Well, the way we write it out is we kind of go by our blocks. So we have the S block here and the P block here. And the S block, that comes first. So for carbon, the electron configuration would be 1s2, because if you look at it, we go 1, 2, right? And then we go 2s2, because we're still not at carbon. So we go again 1s2, 2s2, and then we go over here. So we kind of just write it down until we get to the block or the element that carbon's at. So in this case, if you look at it, we go 1, 2. So that means carbon would be 1s2, 2s2, 2p2, right? And in case this doesn't make complete sense, I'll just do another example. So let's look at phosphorus, which is element 15. So what would be the electron configuration for that? If you guys want to try it out, please pause and do so. But otherwise, I'll just do this for you guys. So we got 1s2 because we're in the first orbital. Then we go 2s2. And then we go 2s2, right? Because we can keep going. And now we see that phosphorus isn't in this row, which means this P block is completely filled up. So we got 2p1 filled, 2p2, 3, 4, 5, 6. They're all filled because phosphorus is still down here. We haven't reached it, which means now phosphorus is first 2s2, and then 2p6, right, because it's completely filled up. And now we go to the third row, right? So here we see that phosphorus isn't here, which means that the S block is also filled up. So 3s2, and then now we're in the P block, the 3p block, where we know phosphorus is. So once again, we just count 1, 2, 3, which gives us 3p3. So that is the electron configuration for phosphorus. Obviously, as you can see, sometimes these electron configurations can get really long, especially if you're looking at elements like Pb or the elements near the bottom of the table, right? Because you're gonna have to go down every single row, 1, 2, 3, 4, 5, 6, etc. So a shorthand that a lot of people use they kind of take the nearest noble gas to that element. So for instance, for phosphorus, if we look at phosphorus here, the noble gas behind phosphorus, or I guess before phosphorus, would be neon. So instead of writing 1s2, 2s2, 2p6, you can just substitute neon. And then just write neon, which insinuates your 1s2, 2s2, and 2p6 orbitals are completely filled. And you just write 3s2 and 3p3. So go ahead and practice writing down electron configurations for other elements in case you guys don't completely understand these concepts yet. And yeah, so we'll move on. So I guess one question we need to understand is, why do atoms form bonds to begin with? Well, that's the thing. So atoms share electrons so that they can achieve lower energy, which is essentially synonymous to being more stable, right? Because think about it. The higher energy you are, the less stable you may be because you're moving around a lot or you just have a lot of pent-up energy, right? Because this is honestly something you can think about, like if you're on a sugar rush. You can't really control yourself. You're just like doing things you normally wouldn't be. And that's kind of similar to atoms as well. So when you're higher energy, obviously you have more energy and you're not as stable. So they form bonds in order to bring themselves down to a lower energy state so they can be more stable. So I'm just going to draw a little graph here that will help me kind of depict this concept. All right, so here on our x-axis, we have intermolecular distance. Which is just the distance between different elements, and potential energy on the y-axis. Now this graph is something you'll probably be able to see in your textbooks as well. And unfortunately, I'm not the best artist, so I will do my best to draw things like not just here, but throughout all of my videos, but sometimes they may not be perfect, so, or not exactly to scale. But in this case, scale doesn't really matter. You just need to kind of understand what I'm going for here. So here is our line or curve. As you can see here, it's kind of asymptotic once you get to this area, which kind of represents the area for zero relative energy, which is not really something we have to worry about right now. So what this graph essentially says is over here, our intermolecular distance is obviously pretty large, right? Which means that the potential energy between those two atoms is pretty low. It's not that high at all because it's near zero. So, but the closer you move, right? So that's this point over here. But let's say we move over here. Now we decrease the distance between them, which means we're also decreasing the potential energy, right? We're getting more negative. And obviously the closer you get from atom to atom, the lower the potential energy is. And here is kind of like the perfect point, the best point for the best distance, I guess I may say, to form a bond, which in your textbooks I believe would be around like 74 pm or picometers, and the energy for that potential energy would be around negative 435 kilojoules per mole. Now these are not values you guys really need to know, but honestly this graph isn't something you need to memorize. The point is the closer your atoms are, the more likely it is to form a bond. But obviously you don't want your atoms to be super close, right? Because at that point, it also, once again, kind of gets harder to form bonds. Why is that? So let's look at a point over here where the atoms are immensely close to one another. So if you remember, atoms aren't exactly like a ball, you know? Like they're spheres, they're depicted as spherical shapes. But at the end of the day, they have electron clouds, or electrons kind of zooming around those nuclei. So if you get too close, the nucleuses of each atom kind of repel one another in a concept called nuclear repulsion, right? This increases the bonding energy, which makes it extremely hard for these atoms to form bonds. So this nuclear repulsion is among the protons in the nucleus. So remember, if you get too close, it's not good either. So there's like a perfect distance, which is, I guess, scientifically determined to be 74 picometers. So if you guys remember from general chemistry or physics or whatever, when you make a bond, you give off energy, right? You release energy to make bonds. Now they are exothermic, because they're essentially losing energy from the system. They're giving it to the system. Now, if you want to break a bond, however, it's the opposite. You need energy to break a bond. So that just means that they are endothermic, because they require energy to break the bond. Right, so next. Now we're going to be talking about how atoms form bonds. Oops, sorry. All right, so the valence electrons, or the outermost electrons in each element, are the electrons that make the bonds, that facilitate the bonding relationship, essentially, between different atoms. Okay, so for instance, let's look at carbon. Right, we already wrote the electron configuration before, but once again, here it is: 1s2, 2s2, 2p2. So here, the 1s2 shell is completely full, right? Because there's no 1p block, it's just 1s. And because we have 2 electrons in the s shell, it's full. But however, this valence, the 2 block is the valence shell in this case, because it's kind of the highest number, I guess you can say. So what does that mean? Well, that just means that this area is where the bonding occurs, in this shell. Because if you remember, the 2p block can have up to 8 electrons, 2 in the s and then 6 in the p, right? So that's 8, which means that carbon is still missing 4 electrons in its valence shell. A lot of people by OChem have learned what Lewis structures are, and Lewis structures are kind of just like structures which show the electron configuration in the valence shell of an element. So for instance, for carbon, the Lewis structure is going to be something like this, because it has 4, because remember, carbon has 4 electrons in the valence shell, and it has 4 electrons here, right? So let's look at other elements. For instance, nitrogen. So if we look up here, nitrogen is 1 to the right of carbon. So logically, that just means nitrogen has 5 valence electrons. Right? So 1, 2, 3, 4, 5. An important concept about Lewis structures is you can't pair electrons until all 4 sides have been full. So you can't do something like, or I guess, hang on, that doesn't make sense. Something like this, 1, 2, 3, 4, 5, right? So I guess when you're drawing them, you can't just really like pair them up until all four sides have an electron in them. Okay, so anyways, and then just one more, oxygen. Oxygen, if we look, has 6, right? Because it's to the right of carbon. So once again, 1, 2, 3. Oh, see, that's what I mean. You can't do that. So 1, 2, 3, 4, 5, 6, right? So now let's look at like how these elements kind of bond. So throughout organic chemistry, these 3 elements, carbon, nitrogen, oxygen, are going to be elements that you see a lot and will form a lot of bonds. But for instance, carbon isn't going to form like a 4-level bond because it can take 4 electrons, right? It's not going to do something like this. There's going to be like common motifs or common like themes of bonding for carbon. So for carbon, that would be something like it's going to have 4 single bonds, or it can have 2 single bonds and 1 double bond. It can have 2 double bonds. Or finally, carbon can have a triple bond and a single bond. See, once again, like carbon is honestly very versatile. You can do a lot of things with it, and that's why there's like an entire section of chemistry or entire subject of chemistry dedicated towards it. So for nitrogen, you can have like 3 single bonds, and then you have the lone pair of electrons up there. You can give it a double bond, a single bond, and a lone pair, or you can use triple bonds. So these are going to be like the most common bonding mechanisms of nitrogen you'll see. Oxygen, something similar. You can have a double bond and then 2 lone pairs, or kind of 2 single bonds and 2 lone pairs, right? So what you guys should try to notice is, if you guys look at the formal charge, which I will cover later in this section, but if you guys are already familiar with that concept, you can see that the formal charge of these elements are all 0, meaning these elements don't have any charge, which is kind of what atoms strive to be. So that's why these are the most common bonding mechanisms for these elements, even though, for instance, oxygen can have something like 3 single bonds, right? Oxygen can have that, but then if you look at the formal charge, that's going to make oxygen positively charged, which is not something that an electronegative element like oxygen really likes. But these are concepts we'll cover more in detail later, but I just wanted to point that out for you guys, in case you're interested. So next, I guess we're going to be talking about formal charge. So what is formal charge? Formal charge corresponds to the difference. So sometimes I'm just going to use shorthand so I can just, write faster. But I will be saying like the word out loud in case you guys don't know what like diff means. So between number of valence electrons compared to number of valence electrons for a neutral element or atom. Valence electrons in a bond. So yeah. So for instance, oxygen. Normally oxygen, once again, the Lewis structure looks something like this, right? It doesn't matter where you put the 2 on. It's just, once again, you have to make sure you just draw it properly, I guess. So which means oxygen tends to have 6 val electrons normally, right? So if we look here, if we look in one of the common bonding structures of oxygen, something like this, let's count up the electrons that oxygen has. So it has 1, 2, 3, 4. A single bond counts as 1 electron for that element. So 1, 2, 3, 4, 5, and because it's a double bond, it's 2, 6. So in this bonding mechanism, oxygen has 6 val electrons, which is the same as normal, right? 6. So what does that mean? It means oxygen doesn't have a charge, which is honestly what most elements kind of want to be like. They don't want charges. So let's look at the thing I drew for oxygen a little while earlier. What about something like this? Oxygen can have 3 single bonds, and then it can have a lone pair, right? It still has a full octet of 8 electrons, but let's count them up. So we got 1, 2, 3, 4, 5. Now oxygen only has 5 valence electrons. So you may wonder what that means. And that just means that oxygen has a charge this time. So in this case, because 6 minus 5 equals 1, positive 1, oxygen would have a positive 1 charge here. And that's all that means. But as you go through chemistry, you'll figure out why atoms don't want different charges, or why they want to be neutral, or why they want to be negative. For instance, oxygen tends to be a pretty electronegative atom, so that's why it would want a negative charge if it has a charge. So a positive charge is obviously not ideal for it. So let's look here at this molecule glycine. If you guys want, pause this video please, and just try to calculate the formal charges of the different atoms, such as nitrogen, this carbon, oxygen, and oxygen. And yeah, just practice. So go ahead and pause if you guys want, and I'll just go over it here. So if we look at nitrogen, nitrogen has 5 electrons in its valence, but here it has 1, 2, 3, 4, right? Which means nitrogen has a positive charge of 1, because 5 minus 4 equals positive 1. Let's look at carbon. We know carbon has 4 electrons in its valence shell, and here it has 1, 2, 3, 4. So carbon's where it wants to be. It has no charge. Let's look at this carbon. 1, 2, 3, 4. Once again, carbon doesn't have a charge because it has 4 electrons again in its valence shell that we look at. So here, let's look at this oxygen, right? So it has 1, 2, 3, 4, 5, 6. And that's what oxygen wants. Oxygen normally has 6, and oxygen here has 6, and it has a full octet. So oxygen here does not have a charge. And let's look at this oxygen finally. So it has 1, 2, 3, 4, 5, 6, 7. So we all know what 6 minus 7 is, right? And that's just -1, which means this oxygen has a formal charge of -1, and this has a positive 1. So I guess side note, you can see that in a molecule like glycine, the positive charge and the negative charge here kind of cancel out, which tend to overall make the molecule net no charge because the -1 and +1 cancel each other out. So next, I guess we will be speaking about molecular orbitals. All right, so what are molecular orbitals? They are the combination of atomic orbitals in constructive or destructive interferences. Right, so this is kind of where we start getting into bonding, or it's kind of where we get into hybridization, which tends to be a pretty complex topic for a lot of people. So first, for instance, we have an atom, right? And the atom has for instance, we're going to talk about hydrogen. So the atom has an orbital, right? The 1s orbital. And then we add it to another atom that has the 1s orbital. Right? So if these two bond, what happens? They're going to share that orbital and they're going to share those electrons. That's their bonding orbital, the molecular orbital. And when something like this happens, when they're kind of sharing it, they are considered constructive. Right? But on the other hand, if you have something like 1s plus another 1s, and you bond them together, you can get something like this as well, where we have something called a node in between, right? See this line dividing them? And these are called anti-bonding orbitals. This isn't really something we'll be covering in detail because it's not something we really look at too much in a college level chemistry organic chemistry course, but I'm just explaining it for the purpose of. And this, when they form anti-bonding orbitals, those are considered destructive. Now let's look at what this means in terms of energy levels, right? So we're going to draw our energy level diagram. So remember, this is for hydrogen, H2. Right, so we have our orbitals, our 1s orbitals, 1 electron in each. This is before the bond. And now we have our bonding orbital, bonding MO, which stands for molecular orbital. Remember, the point of a bond is to move to a lower energy level, to be more stable, right? But for every bonding molecular orbital, you're going to have an anti-bonding molecular orbital. But if you remember from general chemistry, we always fill our lower energy levels first before moving to higher. So we fill the molecular orbital, but we don't fill our antibonding orbital. So even though we have an antibonding for every molecular, it doesn't mean that we're going to actually have electrons in there. So I think the important part here is just to remember that we always have one anti for one bonding, and that the bonding orbital is at a lower energy level than the normal state, whereas the anti-bonding is at a higher energy level, which means the bonding orbitals are going to be filled up first. So let's look over here. So if we look at this, we're going to try to answer a question. So why is methane essentially like our why is methane CH4 not CH2? So for instance, methane has one carbon. It's kind of our simplest like carbon compound, I guess you can say, right? Because it's just carbon and 4 hydrogens. So why is it not just CH2, you know? So let's look at this first 2s orbital. This 2s orbital, obviously we know is filled, right? Because remember carbon is 1s2, which is filled, 2s2, 2p2. Now let's look at this 2py orbital and this 2py orbital, right? So these 2p orbitals are not filled. Okay? And this 2pz orbital is empty, right? So if we look at this, this would be CH2, right? So if we didn't fill this orbital and then if we didn't fill these orbitals and we just had CH2 instead of CH4, the carbon would not be as stable. Would not be as stable as it could be. This is not to say it isn't stable. Maybe it is. I'm not completely sure. But the point is it can be even more stable. So if you can go to an even lower energy level and be more stable, why wouldn't you, right? So this would not be as stable as it could with 4 bonds. So it forms 4 instead of 2 bonds. So that's why it ends up being CH4 instead of CH2. So the next question I guess we need to think about is, why is orbital hybridization even necessary? Right? So the answer to this actually is it's because the atomic orbitals combine to form hybrid orbitals, right? Because they're coming together of degenerate energy. So degenerate is just a term which means same or equal, right? So what this is essentially saying is by hybridizing an orbital, we put them on an equal energy level. So let's look at what this means. So if we look at our energy levels, we have our s orbital, right? And then we have like our p orbital. So for instance, our s orbitals, if we fill our s orbital, we can move up to a higher p orbital. Sorry, the p orbital, remember, has 3. So we fill the p orbital with the electrons we have, then we excite it using photon, right? Remember, because if electrons absorb photons, they can go to a higher energy level. So if we do that, we go from s to, we push 1 electron up, right? So we go from here to 1, 2, 3. Remember, Hund's rule, we got to fill all the orbitals up before we can start pairing them up, right? Now if we hybridize, remember, notice here the p is obviously higher than the s, right, in terms of energy. But if we hybridize, we can form a hybrid orbital called the sp3 orbital, in which all the orbitals are now on the same energy level between the p and the s, right? So essentially now we have 4 degenerate or equal orbitals that can form bonds. So here, once again, we're going to look back at methane. We're building a molecule of methane here. Right, so let's draw this baby out. We're going to use dashes and wedges as well to show 3-dimensionality. So we got our H's, then we have a wedge, which insinuates that this atom is coming out of the page towards us. and dashes, which represent it going into the page or into the plane. So these bonds, these single bonds, are called sigma bonds, right? And they overlap. Or there are orbitals with S character. So like remember S and P? So these sigma bonds are orbitals with S character. So this is mainly sp3 hybridization that we went over here, right? Now let's look at some sp2 hybridization. sp2 hybridization. Okay, so let's look at this. So once again, we have our 1s, right? Let me draw it underneath. 1s, then we got 2s, and then we got 2p, right? So we fill up the 1s, then we can move to a higher 2s. Once we fill up the 2s, then we can actually go to the 2p. So let's fill this up as much as we can. So let's say we go here, right? Once again, we're looking at carbon. Now we excite it with a photon. Oh, you can't really see that, but that says excite, and I used yellow to represent using a photon, which means now we take a 2s, 1s. So this is still full, but now we move, sorry about that, we move one electron from the 2s to the 2p. So now the 2p orbital have all of the orbitals filled up, right? And now we hybridize to form degenerate orbitals. So we have our 1s still here, and then now we have a 2sp2 orbital and a p orbital. So here the p orbital has one, and then we have 1, 2, 3, right? So what we're essentially doing here is we're combining an s orbital with two p orbitals, right? Combined. So once we do that, we get a molecule that looks like this. Now we're talking about p orbitals here as well, right? So if we look at a top-down view, it would kind of just be something like that. This, kind of like a triangle flower thingy, with angles between these orbitals being around 120 degrees. And these would be our sp2 orbitals. So as you can see in this diagram here, once again, you see the top-down view. You're seeing these three sp3 orbitals here, 1, 2, 3, over here. And then obviously we can't really see it from a top-down view, but our p orbitals are essentially vertical. So yeah. So this leads us to talk about pi bonds. Pi bonds. Kind of simply put, I guess, they can be considered like double bonds. So for instance, let's look at a molecule that has pi bonds. Right? So a double bond, something you need to know is that a double bond always has a sigma and a pi bond. Okay? So it has one sigma and one pi. So the sigma bond is due to sp2 overlap using our two sp2 orbitals we have. And the pi bond is from a p and a p orbital overlap. So if we look at our diagram here, we see that we have our anti-bonding, remember, because we have an anti-bonding and a bonding. And we see how they overlap, how our orbitals overlap here. And anti-bonding, because there's a node, they kind of push back and repulse one another, but in a bonding, they overlap with one another. So yeah, so remember, or I guess a quick note is that pi bonds are side to side, whereas sigma bonds are end to end. So I guess this is just another example of that. Over here, we have our pi bonds, they're overlapping side to side, right? But our sigma bonds are going end to end. But yeah. So because if we think about it, our sigma bonds can rotate, but pi bonds can't. Why? Right? So once again, let's draw out an example. I'm not going to be using stereochemistry just for simplicity. Right? But this sigma bond here, oopsies, this sigma bond here, it's free to rotate. But now let's draw a molecule with a pi bond. If we visualize this, we're going to have something, a pi orbital on this and on that atom, which overlap side to side. So think about it. Over here, we can kind of twist this bond, right, and turn those molecules, because it's kind of like a rod attaching them. You can twist a rope, right? But here, we're not just connecting it with a sigma bond. We also have interactions on the top and the bottom here from the p orbitals. So we can't rotate it, because if you think about it, when we try twisting, this interaction are kind of like going to break, you know? So that's why we can't twist or rotate pi bonds. Can't rotate. So I guess simply put, sigma bonds have single point of overlap, right? Single point. But pi bonds have multiple points of overlap, which would break if we try rotating them. So let's look at what happens if we have multiple pi bonds. So that just means a triple bond essentially, because a triple bond has 2 pi bonds, 1 sigma bond. So let's once again draw out the energy orbitals once more. So we got our 2p, and we got a 2s, and we got a 1s, right? So we fill up the 1s first, then we go to 2s, then we fill up the 2p as much as we can. Obviously, we're going to excite, push an electron up. And now we have an electron there. Our 2s orbital has 1, our 1s orbital is still full. And then if we hybridize, we're going to have our 1s orbital still just chilling there. And now we're going to have a 2sp orbital and 2 in the p orbital, 2p. So this indicates that now we have 2 p orbitals, right? Instead of just 1 like we did for a double bond. So here, let's look over here at this electron cloud drawing. Once again, we have our p orbitals, our s orbitals overlapping, right? As you can see with those lines. Now we have the p orbital, that's kind of going vertical, and those are interacting. But now because we have another p orbital or another pi bond, we have a p orbital in another axis, you know? So kind of like in the z-axis if we're talking about an xyz axis. So we have an orbital perpendicular to the other p orbital, and now there's interaction in that pi bond, giving us 2 different pi bonds. So remember, these 2 p orbitals are going to be 90 degrees apart. So now, let's just do a little bit of practice. Hybridization practice. Feel free to copy this molecule down and just, I don't know why I wrote property. Practice. Now feel free to try to, identify the hybridizations of the 4 carbons labeled. And feel free to pause the video while you do that. So I hope you guys answered this question, and now we'll go over it. So this first carbon would be sp2, right? Because it has 3 sigma and 1 pi, right? Because it has a sigma bond, and a pi bond. And remember, a double bond has 1 pi, 1 sigma. So 3 sigma, 1 pi. Now this one would be sp. What does that mean? It has 2 sigma and 2 pi, right? Once again, double bonds have 1 sigma, 1 pi, so it has 2 double bonds, which means it has 2 sigma, 2 pi. And let's look at this third carbon. This third carbon is similar to the first carbon, so it would be sp2 as well, which means it has 3 sigma, 1 pi, right? Because it has sigma, 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 pi. And let's look at this fourth one. So if you drew it out, it would kind of look like that if we drew these 3 H's out. But anyways, the hybridization would be sp3 because we just have 4 sigma bonds, right? So what this means overall is, for over here, this means that we need 4 hybridized orbitals. Here, remember, because p orbitals are p orbitals are unhybridized orbitals. Sigma bonds are hybridized orbitals. So we need 3 hybridized, 1 unhybridized, right? And then you get the gist of it, which means for carbon 2, we need 2 hybridized, 2 unhybridized, etc. So for something, that's sp2 hybridized, so for a molecule like this, right, where we have carbon in the center and 3 bonds, but no lone pair because you can see that there's a formal charge of 1 here, we can say that this would be sp2 hybridized, not sp3, because the remaining orbital that isn't shown, or it doesn't have one right now because of the formal charge, would be unhybridized. It would be an unhybridized p orbital. And so yeah, that concludes our first class, I guess. Yeah, that concludes our first instructional video. So remember, in this video, we went over kind of just like what atoms were, why they bond, and we started looking into some more complex topics such as hybridization. Now, you guys should definitely understand these concepts, and I hope this video really helped with that, because these concepts are honestly really vital towards understanding organic chemistry in a whole, because these concepts are kind of the building blocks for what we'll see later on in this course. So for our next video, we're going to go over electronegativity and bond polarity, which includes dipoles and stuff. So please be sure to tune in. I hope this video was once again helpful. If you guys have any constructive criticism on how I can maybe make this even better, please leave a comment below, like and subscribe if you guys think this is good, so I know how I'm doing. Thank you guys.